Hi, everyone, and welcome to Organic Chemistry on YouTube. Today, we'll be talking about conformational analysis. This will be one of the first episodes on this topic that I've broken down by types of strain energy. But before we jump into a conformational analysis, let's run through some definitions. So a conformer is essentially an isomer of a molecule that differs in the 3D structure by rotation around a single bond. You can also have different conformers that are rings that don't involve directly a rotation around a single bond. So strain is essentially the energy increase of a molecule or structure that comes from deviating from an ideal geometry. Torsional strain is one kind of strain energy. So this is most often seen in eclipsing interactions. You can think of these also as filled-filled interactions. Those are two filled orbitals that unfavorably interact with each other and increase the energy of the molecule. So let's go through an example, one of my favorites. So this is the conformational analysis of butane. So conformational analysis means we're analyzing the differences in structure and energy of two or more different conformers. So let's start off first by just drawing the line structure of butane. It's different conformations, okay? And this one that I've drawn here is known as the antiform. So if we draw a Newman projection, looking down this bond, you can draw this Newman projection. Looking at it from the front, the methyl is pointed down, the wedged hydrogen is pointed to the right, the dashed hydrogen is pointed to the left. In the back, the methyl is pointed upwards, and this is known as the antiform. Okay, if we rotate around this single bond, as invoked by the definition I gave earlier, rotate it by 120 degrees, this is the new molecule in its 3D representation. Okay, so this is a different conformer of this molecule. Translated to a Newman projection, this one is known as a gauche form. We'll analyze the differences between them in a moment, but I just want to go through all these different possible conformations. And then the other one is where we rotate carbon-3 by 120 degrees again. And we translate that into a Newman projection. And one more conformer, which we call the eclipsed conformer, that looks like this. So now let's compare their energies. So we're giving the energies in relative terms. This is 0.0 kcals. The gauche version is 0.9 kcals per mole, higher in energy. And the other gauche form is the same. And then the eclipse form is about 5 kilocalories per mole. So it might be unclear how to really make sense of these energies. Is 0.9 kcals per mole a lot? Is 5 kcals per mole a lot? At 25 degrees Celsius, if you have a difference in energy of 1.4 kcals per mole of free energy, there's a 10-to-1 ratio of the energetically favored structure to the energetically disfavored structure. If the difference in energy is 2.8, you end up with a 100-to-1 ratio, and 4.2 gives you 1,000-to-1. Okay, so when we compare the difference between 0 and 0.9, 0.9 is most of the way to 1.4, so there's a significant preference of the antiform to the gauche form. And even more different is the 5 kcals per mole difference, where it will be more than 1,000-to-1 ratio of anti. A little bit of energy goes a long way in determining the conformational preference of a molecule. Now, let's see why the energies are higher and lower relative to one another. The anti and the two gauche forms are considered to be staggered conformations, which means we minimize torsional repulsion between these three. There's no eclipsing interactions between these molecules. In the anti form, the methyls are as far apart from one another as possible, so that minimizes steric strain while optimizing torsional strain. In the gauche form, though, the methyl groups are a little closer to each other. These two curved lines indicate a steric clash. So those two methyl groups get pretty close to one another. I recommend you build a model to convince yourself of this. And that's worth about 0.9 kcals per mole. In the other gauche form, we have the same steric interaction, but it's just on the other side of the molecule. So these two are symmetrically equivalent, so they're the same difference in energy. And now in the case of the eclipsed butane, we have a 5 kcal per mole difference, which we can dissect. About 3 kcals per mole of that, 3 kcals per mole of this 5 comes from the torsional strain associated with sigma bonds overlapping with each other in this eclipsed way. The additional 2 kcals per mole that we see are due to the steric effects resulting from these methyl groups being as close as possible to one another. Are there any molecules out there that favor torsionally strained eclipsed conformations? Yes, there are. These are usually not covered on the MCAT or maybe reserved for one of the harder questions on exams, but I'll give you an example just so you can see. So in the case of this diol, we have two possible conformers. One where you have torsional strain, the one on the left, we can label this A, and the conformer B, which is torsionally unstrained. I recommend that you make a Newman projection and test your understanding of this, and then come back to the video and try and understand why torsionally strained conformer is lower in energy than the torsionally unstrained conformer. So now when we look at this structure of the torsionally strained conformer, indeed, you have all eclipsing interactions. But when you obtain all those eclipsing interactions, these two alcohol groups are as close as possible to one another. So there you can have an intramolecular hydrogen bonding interaction. So the hydrogen that I'm circling here is being stabilized through an intramolecular hydrogen bond. Because hydrogen bonds are relatively strong, overwhelms the preference for this molecule to be in a torsionally unstrained, staggered conformation. Well, this has been Torsional Strain on Conformational Preferences in 5 minutes or less.